Section 7.13, Trends in Successive Formation Constants. We're talking about the formation constants of this type of reactions. In this reaction, this ligand L replaces one of the aqua ligands bonded to M. So if you compare here and here, this transition metal is now bonded to one more L ligand and one less aqua ligand. And X can be 1, 2, 3, 4 in a tetrahedral complex, or 1, 2, 3, 4, 5, 6 in an octahedral complex. Typically, Kf1 is greater than Kf2, Kf2 is greater than Kf3, Kf3 is greater than Kf4. Why is that? Well, naively, we would think in this Kf1, Kf2, Kf3, and Kf4, and etc., we are doing the same reaction. We are replacing one aqua ligand with one L ligand. So what's the difference? Well, seemingly, there's the same enthalpic effect. However, I want to remind you, when you have just a transition metal bonded to 6 water molecules, and then you are trying to replace one of the 6 aqua ligands with L. There are 6 options, right? And now, if one L is already bonded to this transition metal, you have M with bonded with 5 water molecules and one L ligand. Now, if you're looking at the next replacement reaction, the second ligand, L, can replace only one of the 5 aqua ligands, right? And then if you're looking at the transition metal, now with only 4 aqua ligands and 2 L ligands, the next L has only 4 options. It can only replace one of the 4 aqua ligands, and so on. So finally, if you have ML5 and one aqua ligand bonded to the transition metal, the 6th ligand has only one option. So again, if you just look at the number of available aqua ligands, this number gets smaller and smaller when this M is bonded to more and more ligands already. And now we're talking about the formation constant. This is actually an equilibrium constant. So not only we should look at the forward reaction rate, we also need to look at the reverse reaction rate. And if you look at the reverse reaction rate, it also depends on the number of ligands of L that are already bonded to M. All right. So in the reverse reaction, we replace one L ligand with one aqua ligand. So that means if you have a larger number of X, and then the reverse reaction rate is going to be greater. So now we have 2 reasons. When X increases, the forward reaction rate is reduced. Meanwhile, the reverse reaction rate is enhanced. So both reasons result in a decrease of the formation constant, because again, the formation constant is the forward reaction rate divided by the reverse reaction rate, right? The forward reaction rate constant divided by the reverse reaction rate constant. So if you look at the forward reaction rate constant, it decreases as X increases. And on the bottom, the reverse reaction rate constant increases as this X increases. So both reasons result in the decrease of the equilibrium constant of this formation reaction as this number X increases. Now let's do a more quantitative analysis. So let's look at just a octahedral complex. There are 6 formation reactions. from M to ML, from ML to ML2, from ML2 to ML3, ML3 to ML4, 4 to 5, 5 to 6, 6 on them. And then if we just look at the number of aqua ligands on the left-hand side, because that determines the forward reaction rate. So over here, this M is bonded to 6 aqua ligands. So, and this one, 5 aqua ligands, 4 aqua ligands, 3, 2, 1 aqua ligands. So if you look at this forward rate constant, the ratio is going to be 6 to 5 to 4 to 3 to 2 to 1. So this ratios are proportional to the number of available aqua ligands to be replaced. Now let's look at the reverse rate constant. In this case, when we're talking about the reverse rate constant, we are replacing one L with one aqua ligand. That means we need to count the number of available L ligands. So it's 1 here, 2 here, 3, 4, 5, 6. So over here. And then the ratios between those reverse reaction rate constant is going to be 1 to 2 to 3 to 4 to 5 to 6. So we got two ratios. All right, this is forward, this is reverse. And then we use forward divided by reverse. 6 over 1 is 6, 5 over 2 is 2.5, 4 over 3 is 1.33, 3 over 4 is 0.75, 2 over 5 is 0.4, 1 over 6 is 0.17. And then we can take the ratio between those formation constants, those successive formation constants. So 2.5 divided by 6, that's 0.42, and this divided by this, 0.53, 0.75 divided by 1.33, that's 0.56, and so on. So we got all those ratios between two successive KF. So this is actually KF2 over KF1, KF3 over KF2, KF4 over KF3, KF5 over KF4, KF6 over KF5. And all these ratios are lower than 1. So that's why typically KF1 is greater than KF2, greater than KF3 and 4, etc. due to these two statistical reasons. All right, but this is just theoretical prediction. The numbers are here, 0.42 here, 0.53 here. So over here, those 5 ratios between two successive formation constants. What about experimental values? Well, let's look at one example. Over here, you have this nickel transition metal center bonded to amine ligands and aqua ligands. So we have 6 formation constants, and we can take the ratio between KF2 and KF1. That's 0.28, and then KF3 over KF2, 0.31. So we got these numbers. Now let's compare this 5 numbers, this 5 ratios with this 5 ratios. Well, they are different, but at least I want to say these ratios are smaller than 1. These ratios are also smaller than 1. And also, if you just, in general, look at the trend, the middle 3 in general is greater than the first one, the last one. The middle 3 is in general greater than the first one and the last one. So in general, they agree with each other semi-quantitatively. So now let's look at some anomalies. So it's possible to observe this reversal of this inequality. Well, in that case, if KFN plus 1 is much greater than KFN, that indicates a major change in the electronic structure of the transition metal complex. So again, supposedly this is true for the formation constants for most transition metal complexes. But then if you see a reversal of this, that means if this number is much greater than this number and there's some other factor. So now let's look at this 3 reactions. So over here, this iron transition metal center is bonded to 6 aqua ligands. Now we're going to use bipyridine to replace 2 waters at the same time. Bipyridine is bidentate. So over here we have this formation rate constant. This is really 10 to the power of 4.2. And then let's replace the next two aqua ligands with one more BPY. This formation constant is 10 to the power of 3.7. So that's good. This is lower than this. Again, this is 10 to the power of 3.7. This is 10 to the power of 4.2. We are talking about the logarithm with a base 10 here. All right, so that makes sense. But then if you look at the next one, now we're going to replace the last two aqua ligands with a BPY. In this case, this Kf formation constant is 10 to the power of 9.3. So this is much greater than this. This is about 10 to the power of 5.6 factor greater than Kf2. It's nearly 1 million times greater. So what's going on here? Well, there is a significant change in the electronic structure in the transition metal complex. So in this structure, later in chapter 20, you will see this ion, hexa aqua ion, has a high spin electronic state with respect to the ions. All right, so there are actually 4 unpaired electrons. So remember, when you put 6 electrons in the 5 different d orbitals, the high spin state means we maximize the number of alpha electrons, right? Well, you can also choose to maximize beta electrons. They are kind of equivalent to each other. But just for convenience, let's try to maximize the number of alpha electrons. The goal is to maximize the number of electrons with the same spin to maximize the magnitude of the so-called exchange energy. So in that case, when you put 6 electrons into 5 different d orbitals, there will be 4 unpaired electrons with the same spin. It's favored by Hund's rule because that will maximize the exchange energy. Why is that? Well, this is simply because when 2 electrons have the same spin, they cannot occupy the same spatial orbital. And that will effectively reduce the repulsion between these 2 electrons. So given the same other conditions, the repulsion between 2 alpha electrons is smaller than the repulsion between 1 alpha and 1 beta electron. So really, if you have maximized the number of unpaired electrons, you minimize the repulsion between those electrons. Now, however, in this structure, you will learn again in chapter 20, this is bipyridine. When 3 bipyridine bidentate ligands are bonded to this iron transition metal center, now this D6, the 6 d electrons, prefer to adopt a low spin state. Now we have 0 unpaired electrons. We'll talk about the reason. The 5 d orbitals actually split with 2 orbitals lying above the 3 others. And then the off-ball principle tells us we need to occupy the lower energy orbitals first. So now this time we're going to put all 6 electrons into the 3 lower energy d orbitals. So all 6 electrons are paired. Okay, we'll talk about the reason in depth why. In here, this is high spin state, and in here, this is low spin state. Again, this is because the splitting between the higher energy d orbitals, 2 of them, and the lower energy orbitals, 3 of them, now is much more significant than in the water cases. All right. So because of that, because of the dramatic change in the electronic structure of the transition metal complex in this situation, we have a much larger formation constant. So this is more energetically favored. There's a contrasting example. So we know this Kf n plus 1 should be smaller than Kfn due to statistical reasons, But sometimes this KFN plus 1 is just so much smaller than KFN. There's got to be some other reason. So in this case, if you look at this 3 consecutive formation constants from 10 to the power of 6.7, 10 to the power of 6.48, now to 10 to the power of 0.95. So again, if you compare these two formation constants, their logarithms differ by roughly 6. That means, again, these two formation constants differ by a factor of nearly 1 million. That's a lot. So why is that? Again, let's just look at this situation here. Over here, you have 1 chlorine replacing 1 water. Again, you have 1 chlorine replacing 1 water. But now, what is also going on is here. Look at this subscript. You have 4 aqua ligands bonded to mercury. Only 1 aqua ligand bonded to mercury. So this chlorine minus did not just replace 1 aqua ligand. This chlorine minus replaced 3 aqua ligands. And why is that? Well, very simple. Chlorine minus has many lone pair electrons, and they tend to repel each other strongly. So over here, you have a fairly strong repulsion between those ligands when you have more chlorine minus bonded to mercury. So in this case, now this mercury prefers to form only 4 bonds, and this is roughly a tetrahedral structure. And since you are breaking 3 mercury alcohol bonds instead of just 1, energetically it's disfavored. You are breaking 3 bonds, and as compensation, you're forming only 1 mercury chlorine bonds. So that's why this KF drops significantly. All right. But then we have another anomaly here. In this case, let's look at this reaction. We are talking about using bromido ligand to replace aqua ligand here. And now let's look at this formation constant. 36.3 and 3.47. Those are the absolute values. Those are not logarithms. So these numbers are fairly close to each other. And then the third formation constant, 1.15. The fourth one is 2.34. So this one is a little bigger than this one. All right, and why is that? So if you really look at the last formation reaction, this bromido will replace, again, not just 1 aqua ligand, but all 3 aqua ligands. So supposedly, if we are breaking 3 bonds here between cadmium and the 3 aqua ligands and form only 1 cadmium bromido bond, supposedly it's disfavored energetically. It is true. It is disfavored energetically. So supposedly this number should be smaller than this number. But also there are reasons. Bromido is even bigger than chlorido. So over here, if you simply replace 1 aqua ligand, the repulsion between all 6 ligands, now you have 4 bromido ligands and 2 aqua ligands, and it's octahedral, and the repulsion between these 6 ligands is so significant that losing 2 more aqua ligands is favored energetically. So again, there are 2 factors here. It is true, now we'll have to break 3 bonds and form only 1 new bond, but also the steric effect prefers this cadmium to form a tetrahedral complex with just 4 bromido ligands. So overall, that's why KF4 is greater than KF3. But because of this breaking of 3 bonds, so KF4 is not much greater than KF3. It's just slightly greater than KF3. There are so many factors. So for this reaction, first you talk about statistical factors. And that means, well, this KF4 is supposedly smaller than this. And then you look at the bond breaking and bond formation. That suggests this KF4 should be much smaller than KF3. And finally, you look at this steric effect. That suggests this reaction should have a larger formation constant than the KF3. All right, so there are three factors that you have to take into account.